Hello everyone, this is Hank. I'm back. Today I'm going to talk about aperture in photography. Everything you ever needed to know about aperture. Okay, so by the way, I've been told that I speak too slowly. I try to speak faster, but it's not going to work. So if you find it to be the case, if you don't mind, play this video at 1.5 speed. It'll help. Thank you. Okay, without further ado, let's get into our talk. Okay, when we talk about aperture in photography, we immediately think about the exposure triangle, because aperture is one of the three factors that would determine the correct exposure for your photograph. Okay. Today we are going to talk about just the aperture. I'm going to save shutter speed and ISO for a different video. So, a word of warning, you're going to know more than you ever wanted to know about aperture after this recording. So, bear with me. Alright. So, let's talk general first. Okay, we set the aperture. Obviously, we use aperture to control the amount of light that we let into the sensor of the camera through the lens. Okay, but normally we set the value for the main purpose of controlling the depth of field of the picture. So I'm going to show you like a series of 4 pictures with different aperture values for the same scene to show you the effect of aperture. So the first picture here was taken at f2.0. Okay, so at f2.0, note the blurriness of the background, what we call bokeh. Okay, as I increase the aperture value to f4, so you can see the blurriness decrease a little bit, so the bokeh is not as creamy. As I increase it more, you will see the background more clearly because the depth of field is being increased by us changing the aperture value. Now further, I change to f16. It's going to be a lot clearer. So basically, aperture control in turn control the depth of field. So we all know that. Alright, for practicality, we may want to blur the background because when we take a portrait picture, we are interested in the model and not so much in the background. So therefore, if we blur the background, we bring more attention to the model. Okay, so in these two examples, I took the one in the left at 1.8, took the one on the right at 1.4, and give me the creamy, blurry effect in the background. Okay, on the reverse, right? So in this picture here that I took of Convict Lake in California, I wanted everything to be in focus, so I set it to f16, and I achieved that by a really deep depth of field. Similarly, here, this picture I took at the Horseshoe Bend, and I also set it at f16, but I want to bring the attention to you that at a higher aperture value such as f16, what you can do is to create a starburst effect. Whenever you have a really bright source of light, in this case the sun, you will get starburst effect. Okay, with that, we are now going to get into the really nitty-gritty part of the talk, which hopefully you're interested in, otherwise you wouldn't be watching it until this point. So by definition, aperture is the size of a lens opening. Okay, so as you can see in this picture here, a series of pictures rather, that shows you the lens opening versus the aperture values set. Okay, so you have a larger opening here, and it gets smaller and smaller as the value increase. You may have noticed that the value, the smaller the value, the larger the opening, so it is the opposite effect. Think of it as a ratio. That's why you have the slash. It's 1/. It is a ratio. Okay? So that dictates the size of the opening by various numbers of values. Okay? The larger the opening, the less depth of field you're going to have. And this is just like our eyes, Our eyes, when it open big, your depth of field is less. And that explains it for some people. When you go out at night, you can't see as well as you during the day. The reason is, the eyes has to open big. So basically think of this as a very small aperture value, very large opening, and your depth of field is not very deep, therefore you can't see very well. Alright, the reverse is true. During the day, your eye gets smaller and then you can see depth of field is really deep. Okay, so let's get back to this. The aperture is represented by a series of numbers that at first look doesn't seem to make any sense. Okay, the numbers are not even, Go from 1.4 to 2.8, F4 and all that, and we're going to explain that a little further in the next slide. Okay, so let's do that. Okay, before I do that, each of the numbers does have a meaning. You don't have to really remember exactly, but the idea is this. Okay, there's a relationship between the lens focal length and the aperture value, that being the diameter of the lens opening. What I'm talking about is, if you take the lens focal length, right, you divide it by the aperture value that you set, or the aperture value that the widest aperture, meaning that the smallest aperture value of your lens, that will dictate the diameter of the opening that your lens have to have. Okay, take this example here, this picture here. Okay, this is a picture of me. This was me about 10 years ago, me about 3-4 years ago, and me today. I'm getting older and older and older every time. But anyway, this is the same lens, just different covering. I used to have this, and now I have this Woodlands scheme, but it's the same. My favorite 600 f4. So basically, you ever wonder why this thing is so big? It's big because of the physical property that the lens have to have. Okay, at least for this kind of lens, Canon makes a DO lens that don't use this physical model, so it might be different, but 99% of the lenses that we use today is using this formula. So basically, in order for it to be a 600 millimeter at f4, okay, so you take 600 and divide by 4, the diameter has to be 150 millimeter, and that translates to almost 6 inch across, and that is just the opening. You got to build the structure around that. Therefore, the final diameter of the lens is huge, and that's why you see this lens so big. It's because of the physical property that it has to obey. Take the focal length, divide by the aperture value to get the diameter. So I don't know if you know this, but I didn't know this until I learned about it. So it's pretty interesting and has a special meaning for me. Okay, so let's revisit the numbers. What do these numbers mean? Okay, these seemingly random numbers are not really random at all. Okay, so when we talk about aperture value, you often hear the terms f-stop that is associated with the aperture and the exposure triangle, really. But it is controlled, also by the aperture. So when we talk about f1.4, okay, we are basically saying that, hey, I put a 1 f-stop onto the lens. Well, put it this way. The ambient light that exists at the moment, okay, if I set my lens to f1.4, I'm basically cutting that amount of light in half. Okay, so my aperture value of 1.4 is 1/4 f-stop, and I'm cutting the light in half. So only half of the light, ambient light, will be able to get to my sensor through the lens. That's what it means. Okay, if I set it to f2, I cut it in half again. So basically, I cut the ambient light by 4 times by setting it to f2. Okay, when I get to 2.8, I already cut it down to 8 times the amount of light. Okay, so basically I'm like just choking off the light as my aperture value gets bigger. And the size of the hole gets smaller. Okay, so it is a reverse relationship. So I'm cutting the light down in half each time I change the value here. So the value from 1.4 to 2, that means that I cut the light in half. 2 to 2.8, I cut it in half again. 2.8 to f4, I cut it in half again, and so on and so forth. Okay, so now, actually somebody had asked me this. So they asked, like, if the light amount is half, why is the number not double? So why is the number goes from 1.4 to 2 instead of 1.4 to 2.8? That's a pretty good question, actually. But if you think of this physical thing, now look at the size of the holes here. Okay, the size of the hole represents the area of the hole. Okay, right? So when we talk about the aperture value, it is a relationship between the diameter of the hole and the focal length. So the numbers here represent the diameter and not the area. And I don't know how much you remember about math. I kind of actually have to look it up, even though I'm an engineer by training. So the area of a circle is pi multiplied by radius squared. So you take the radius, not diameter. So you take diameter, divide by 2, you get the radius. And then you square the radius, and then you multiply by pi, which is 3.14, to get the area. Okay, so when you half the area here, you don't half the diameter. Okay, you do it at a ratio, and that kind of explains. So because the radius is squared, okay, these numbers are actually the square root value. I will explain a little bit more in the next slide, but you see, you get the idea. The relationship of the aperture value is based on diameter, while the size is based on area, which is diameter squared, half diameter squared to be correct. All right. So that's why the numbers are seemingly random, and they don't seem to make any sense because they had gone through a square root process. Okay, I'm sorry, we're gonna get even deeper. I titled this For the Engineer in Us. By training, I'm an engineer. I've been working as an engineer for the last 40 years. I recently retired, so I have more time to talk to you guys about these things. But so I have to get deep into this, and hopefully you don't mind. But anyway, I look up the formula for calculating f-star, and surprisingly, the formula is very simple. It's for an aperture value, okay, you take the square root of 2 and multiply by the n number. The n number defined as a stop number. So if you let all the light in, you have no stop, so that would be a 0. You let half the light in, that's 1 f-stop, right? So the number is 1. You let 1/4 of the light in, your n number is 2, and so on and so forth. I hope that makes sense. Okay, so you plug in the n number to square root of 2, okay, and you will get the numbers that you will get. Okay, so if you put in 0, you get f1. Okay, believe it or not, some manufacturer actually build a f1 lens. Very impractical because it's probably too big, but it is possible. Okay, most practical one would be 1.2, 1.4. So let's talk about 1.4 because it's the most popular, like 85 millimeter f1.4. Everybody makes one of those. So with a 1.4, that's a 1/4 f-stop, meaning that you only let half the amount of light into the sensor through the lens. Okay, so f-stop, the n number is 1. You plug it in square root of 2 to the 1 power, you get 1.4, and that's why you got a weird number, because it got square root. Square root of 2 is 1.4. And then you plug in 2, you get f2. Plug in 3, you get 2.8. You plug in 4, you get 4.0. That's basically what your f-stop numbers are, the aperture value. Okay, now make things more complicated, right? Our cameras by default allow us to work in 1/3 of a f-stop, not the full f-stop. You can program it to do half a f-stop, but if you don't do anything, it's 1/3 of a f-stop. So therefore, luckily you can plug in the n number. Like here's this chart here, I break it down to 0.3, 0.7, 0.1. So 3 1/3 f-stop before I get from 0 to 1. And I just move on all the way up to n11. Most lenses stop at f22, right? So n would be 9. Right? But you can calculate it using this simple formula to get the aperture value here. So I hope all of that kind of makes sense to you. Why the numbers are so messed up, because they square root based. Okay, and to review the aperture value. Okay, you take that and you multiply it by the diameter of the lens opening, and you get the focal length. Or you take the focal length, divide by the aperture value, you get the diameter of the opening. So there's a distinct relationship that these things work for. So with that, I hope that make a lot of sense to you. And this is too much in the minutia. You don't really need to know any of this, but it's kind of fun to know anyway. But anyway, if you like this, I would appreciate a like from you. If you haven't subscribed, appreciate a subscription from you. And with that, I'm signing off. Thank you very much. Have a good one.